Hello everyone, welcome to our channel Chemistry Academy for IIT JEE and Neet. Today we are going to discuss one of a very important question which appeared in Ioqc 2021 part 2. It is a wonderful combination of ester hydrolysis mechanisms which have been asked in this particular exam and are also relevant to JEE. In fact, the part of this question has already been asked in JEE 2020. So let's move on to the question. This particular question was in fact a 14 marks question. First, let us read the question. Many sweet smelling compounds contain an ester functional group, RCOR-, where RR- alkyl aryl groups. Hydrolysis of an ester is an exhaustively studied reaction. RCOR- plus water forming RCOH and alcohol. The hydrolysis can be catalyzed by an acid or a base. The reaction may be unimolecular or bimolecular and may involve breaking of acyl-oxygen bond or alkyl-oxygen bond. Thus, there are 8 different mechanisms possible as listed in the table below. First, let me explain what has just been written in this question. See what has been said that when you hydrolyze an ester, ester is RCOOR-, right? So, if you hydrolyze, you get acid or alcohol. But there are 2 possibilities of bond fission. For example, if this bond is broken, then acyl and oxygen are separated and then it is called acyl-oxygen bond fission. If oxygen and alkyl, this side of bond is broken, then it is called alkyl-oxygen bond fission. And so does their representations different. Acyl oxygen will be represented by AC, alkyl oxygen bond fission will be represented by Al. Second point to be considered is whether the reaction is carried out in acidic or basic medium because it is catalyzed by both. So if the medium is carried out in acidic medium, then we use symbol capital A. If it is B, then it indicates that the medium was basic. Third point to be considered is molecularity of the reaction. Now, molecularity of the reaction, I assume that you all have already studied kinetics. Molecularity of the reaction here is of the RDS, that is the rate determining step, slowest step in the mechanism. If only one molecule is involved in that mechanism, then the reaction will be termed as unimolecular and 1 will be used to symbolize it. If 2 molecules are involved in the slowest step RDS of particular mechanism, then 2 will be used in the symbol and the reaction will be termed as bimolecular reaction. Let me explain. After considering all this, if you find AAL1, then what does it mean? This A will indicate that the medium is acidic, the reaction is carried out in acidic condition. This will indicate that the reaction is unimolecular, and Al, this indicates that the bond which has been broken for carrying out the hydrolysis reaction is alkyl-oxygen. Second representation, if you find somewhere BAC2, then these are the IUPAC representations. This will indicate that the reaction is carried out in basic medium. This indicates that the molecularity of the reaction is 2. It is a bimolecular reaction, and this indicates that it is acyl-oxygen bond fission which is carried out, which is observed in the overall hydrolysis. So as you can see, there are 3 conditions: acidic, basic, molecularity, and alkyl or acyl oxygen bond fission. So by the combination of all these 3 possibilities, we have 8 possible mechanisms, of course theoretically, for ester hydrolysis, which you can see on screen. You can have unimolecular and acid catalyzed में AAC1 or AAL1. If you go for a bimolecular consideration, AAC2 or AAL2. If you take base catalyzed, then again unimolecular BAC1 and BAL1. Bimolecular is BAC2 and BAL2. So this is how the overall mechanism is. The most common mechanism of all of these which have been observed is AAC2 or you will come across BAC2. These 2 mechanisms will cover almost 90% of ester hydrolysis. As far as our syllabus is concerned, these 2 are more than enough because NCERT has mentioned only these 2. But you must know that there are overall 8 possible mechanisms. Now I'll scroll down to the actual question which appeared in the Ioqc 2021 paper. This is the total question based on the mechanism that they have mentioned. We have to solve all these. Now that is the difference between an Olympiad and JEE or any other objective based competitive exam. These all questions require lot of patience, enthusiasm to solve these step-by-step questions, and definitely it needs a proper instinct sometimes that which direction should I go and solve the question, which comes definitely by thorough study of the subject and practice of questions. So I'll not read out each and every part now. I'll just scroll down. If you need to read, you can pause the video and check the question on your screen. 2.1, 2.2, 2.3, 2.4, 2.5 and 2.6. Total the question had 6 sub-questions, and 6 sub-questions may have further smaller sub-parts. So let us start solving 2.1. Now the 2.1 question, let us read here, it says, consider the acidic hydrolysis of methyl pentanoate in aqueous H2SO4. Draw the structure of the most favorable conjugate acid. Now here, though I have already drawn, I'll read it with you. Do not rush. Please be with me while solving the question. Here I have drawn the structure of the methyl pentanoate as given in the question. As you all know, it is a resonating structure, and you will have these 2 resonating structures for methyl pentanoate. This drawn downside, this one is its resonance hybrid, and this resonance hybrid is the actual structure which will decide its characteristic chemical behaviors. So you can see in this particular hybrid that the negative charge appears on this particular double bonded oxygen. So definitely wherever the del negative is appearing in the hybrid will be the center at which H plus will be attracted. So this is our basic center. At this side I will add the H plus. After adding the H plus, you can see I am getting these 2 resonating structures again. I simply added the H plus over here. I got oxygen with plus polarity. It can have resonance, so you can have plus over here. Out of these 2, you can answer any as the structure of D as a most favorable conjugate acid, or you could best answer it as a hybrid of these 2. That would have been the best answer. So this was a very simple part. Now let's start with the second subpart of this 2.1 question. Question says D is attacked by a water molecule, which is a nucleophile here, and through a series of reactions is broken into a carboxylic acid and an alcohol. Identify the species E, which is a neutral molecule, F and G both being a charged species. So this D we have already drawn in 2.1. This is our protonated ester. On this, water is attacking. Water will attack at this particular carbonyl carbon because due to resonance, this carbonyl carbon will have del plus. After the attack of the water, we'll get this species in which this oxygen is bearing a positive charge. This oxygen bearing a positive charge, it says that it loses H plus, so we'll get a neutral species E like this. Now this again accepts H plus. Here I am accepting H plus at CH3O site. This oxygen is accepting the H plus. See, this part is becoming methanol. Now it loses a neutral species and forming alcohol methanol, and the protonated OH is again losing H plus. This H will be lost, and the final answer is acid. So this particular part of the question is a mechanistic question, and in this, which mechanism is covered, let me tell you. As you can see, this is the RDS of the reaction in which 2 molecules, molecule 1 and molecule 2 are involved. One is the protonated ester, other is the water, and the bond which is finally broken is acyl-oxygen catalyzed by acidic medium. So it is an example of AAC2 mechanism. Moving to next question, 2.2. 2.2 says in the hydrolysis of K is here. In moderately concentrated aqueous H2SO4, the preferred mechanism involves conjugate acid L. This time we have to draw the conjugate acid of this particular K. L undergoes decomposition to form stable product M and a cation N. Already said that N is going to be a cationic intermediate. N on reaction with water will form P. This is formed after the reaction of this N with water. It again has three subparts. Draw structure of LMNP. Identify the slowest step in the reaction mechanism, that is RDS is being asked. Then using the table in page number 4 that we discussed on initial page, label the above reaction mechanism properly, whether it is AAC2, BAC2 and all those things. So moving to the solution. The structure given is this one. This one. Now the important thing here in this structure is that this part is a 3-degree alkyl part. Tertiary butyl part is there in the question. Protonation again we took at the particular oxygen where the hybrid is having a del negative. After that protonation we got this L, which is a positive species. As mentioned, it is formed after acceptance of H+. Now this species is forming a cation. So this is a stable cation. Here you should notice that the bond which is broken is alkyl-oxygen. Alkyl-oxygen bond is broken and you are having a cationic species formed here as a tertiary butyl carbocation, which is very stable. So this is N. The leftover part which is there is this acid which is mentioned as M in the question. Now the mechanism is under acidic conditions. This is the slowest step. I just marked step number 2, and the bond fission involved is oxygen and alkyl, so it is an example of AAL1. So this part is AAL1. Using the table we have to answer, so it is AAL1. Slowest step RDS, we have mentioned that it is the step 2. This is which is the RDS. Now first part LMNP, so we have just reached L and M and N. Now let us move to P. Now this carbocation formed is attacked by water. So water here is acting as a nucleophile. It has a lone pair attacking on a carbocation, forming this protonated alcohol. This when loses H+, then we have a tertiary butanol P. P here is tertiary butanol. It is an alcohol and loss of H+. So this was part 2.2. Just to save time, I have written almost all the mechanism in advance. I hope that would help saving your time. So let us now move to the question 2.3. An optically active sample of ester. Optically active. See, this particular carbon is chiral. So that is why the ester is optically active. Is completely hydrolyzed under aqueous acidic conditions. You can see that again the alkyl part of this particular ester is a 3-degree alkyl part. And whenever it is a 3-degree alkyl part, it can form a stable carbocation. So this example is again going to be, as already said, that H2SO4, so acidic medium, you will have a alkyl-oxygen bond fission and carbocation is formed, so most probably it is going to be Al1. We'll confirm it in the mechanism further. In the hydrolysis, using moderately concentrated H2SO4, two additional compounds R and S, which are other than the expected alcohol and carboxylic acids having identical molecular formula, are formed in small amounts. Draw the structure of R and S. When the hydrolysis is carried out in aqueous ethanol containing H2SO4, another compound T, which is not an acid or alcohol or ester, is also formed. Identify this T. So let's proceed. Assuming that you already know how the resonance hybrid works, this is the ester which is given in the question. In its hybrid, again I will have del negative at this particular oxygen. So directly we are protonating that oxygen and forming a conjugate acid. As we have discussed that this particular is a 3-degree alkyl. This chiral carbon is going to be a 3-degree alkyl. So we will have this bond to be broken and a stable 3-degree carbocation is formed. This 3-degree carbocation will definitely undergo elimination reaction because the alkenes formed are stabilized by hyperconjugation. Now here that you may think, why not a minor product is also considered? Well, as the question said that they have formed two different products with the same formula and did not mention anything about any other product. So under such statements, you should consider only major products as far as possible. So that is why we have taken this. These are R and S, which is mentioned in subpart first. Draw the structure of RNS. Moving to second part, which says that a compound T is formed. How that compound T is formed? Well, the carbocation which was formed 3 degree is under the conditions of alcohol. Alcohol, like water, can also act as a nucleophile. So when alcohol attack on this 3 degree carbocation, then you will have this protonated intermediate. And when this protonated intermediate loses H plus, then this T is formed, which is ether. So the T is ether. As you can see, when the hydrolysis is carried out in aqueous ethanol containing H2SO4, another compound T, which is not acid, not an alcohol, not an ester. Yes, because T we just explored is ether. So this was 2.3. Moving to further, hydrolysis of U is difficult under normal reaction conditions, mostly likely due to bulky methyl groups near the carbonyl group. The ester is hydrolyzed by dissolving in concentrated H2SO4 and then pouring the reaction mixture into a large excess of cold water. Draw the structure of cationic intermediate V and neutral compound W formed in the concentrated acid before pouring into water. Okay, we have to also consider the cationic intermediate and then the neutral compound W, which is also formed. So what is very important to be noticed in this particular compound U is this carbonyl here is sterically crowded. By what? By these two orthomethyl groups. So this time I cannot have attack of nucleophile on this carbonyl carbon and convert its hybridization from sp2 to sp3. So this is an important point that you need to notice before solving this question. Let us start. So as I said that I would avoid attack on this part as it is already crowded. Now this oxygen, other oxygen which is OCH3, is attacked by H plus and an intermediate, cationic intermediate is formed. Now this intermediate loses methanol, neutral species, and a cationic species is formed. As it says, a cationic intermediate V is formed. Now if you pour this particular cation V in water, then again water will act as a nucleophile, will attack over here, and here carboxylic acid will be formed. COOH will be formed. That is what is being said. The ester is hydrolyzed by dissolving in constant H2SO4 and then pouring the reaction mixture into large excess of cold water. That finally will form acid, but we had to report this V in this particular question. Let us move to question number 2.5. J 2020 asked about the hydrolysis of the same X that year. When ester X is dissolved in constant H2SO4 and the mixture is poured in water, an unusual product Y is obtained, which is neither an acid nor an alcohol. Draw the structure of Y. It is again the same type of compound which is sterically crowded at carbonyl. So same theory that I cannot attack water over here. That is not possible due to steric factors. So again attack is on this side oxygen or the OCH3 oxygen. Now when this particular O is protonated, we will have this protonated intermediate. This methanol will leave and we have a very stable carbocation. This particular species is a very stable carbocation. As you can see, it is already an octet complete resonating carbocation. Besides that, you can also have resonance with so many benzenes. Anyhow, this positive, this carbocation formed here is an electrophile and benzene undergoes electrophilic aromatic substitution. Here it is the acylation which is being observed. It is an intramolecular acyl substitution. So now after attack you have got this new carbocation which is resonance stabilized with the benzene. But regain of aromaticity is to be done, so we will lose this H plus and again a neutral molecule is obtained. This is that stable compound which is mentioned in the question. The question says an unusual product because of intramolecular electrophilic attack. They are mentioning that an unusual product Y is obtained. This particular compound is an indigo colored compound. It is a very brightly beautiful compound. Moving to last part of this question. An ester can also be hydrolyzed by heating with aqueous NaOH followed by acidification to yield the carboxylic acid. For alkaline hydrolysis of ethyl benzoate labeled oxygen with O18, the rate of hydrolysis depends on the concentration of both ester and alkali. That simply indicates that it is a bimolecular reaction. Question also mentioned it is a basic medium reaction. So we have got that it is going to be something B and 2. We have to fill, is it AC or is it alkyl? Let's see. Now it is said that this ester hydrolysis some intermediate Z1 on hydrolysis Z2, Z3, Z3 again on H plus acceptance form Z4. Draw the structure of the species products Z1 to Z4 along with the label of O18 using the table on the page number 4. Label the above reaction mechanism properly. We have already started labeling. We just have to fill this particular acyl or oxygen bond fission. So let us predict what could be the mechanism. Ethyl benzoate is given in the question. Base is attacking, so directly on this carbonyl it attacks. OH minus is attacking and anionic intermediate formed is like this. But carbonyl energy or carbonyl bond energy being very high, when this bond reverts, then C2H5O minus is lost. This C2H5O minus is a stronger base than benzoate. So what happens is it abstracts the H plus and ultimately we'll have a benzoate as an anion and ethanol as neutral species. And as you can see, O18 is a part of alcohol. So you can say that the bond which broke was acyl-oxygen. And then this accepted H plus, Z3 was mentioned to accept H plus, forming a neutral Z4. So let us conclude the mechanism is basic medium. You saw it is acyl-oxygen. Question mentioned that it is a bimolecular reaction. Again the RDS is this one when ester and base both are involved. So BAC2 is the mechanism of this particular question. So this was the Ioqc 2021 part 2 question. I hope you liked it, and if you enjoyed the discussion and were benefited by this, please subscribe our channel for more contents like this. We'll keep solving such Olympiad questions on and off. Thank you.